Hello and good afternoon, everybody. This is my keynote speech in the International Conference on Advanced Technology and Applied Science, the ICATAS 2020. My name is Dr. Mohammed Walid Fakhr. I'm a professor at the Computer Engineering Department, College of Engineering, Arab Academy for Science and Technology and Maritime Transport in the Cairo branch. The title of the speech is Data Science and Machine Learning Efforts in the Fight Against COVID-19, a Kaggle Challenges Perspective. So the agenda of this talk, first it will be an introduction of the Kaggle and why I chose Kaggle and the COVID-19 efforts in general, and then a classification of COVID-19 Kaggle challenges, which are 4 of them: forecasting challenges, data analytics challenges, image classification, and image segmentation challenges. And then I'm going to talk about, in each of them, of course, I will talk about the nature of the challenge, the nature of the data, the objectives of the challenges, and the best couple of techniques that proved to get the best results in each of these challenges as a sample of what the data science and machine learning techniques can do in this domain. And then I will talk about the COVID-19 Kaggle data sets in general. And then what is beyond Kaggle? Because Kaggle, of course, is one platform. There are other platforms and other places where people publish and do a lot of work. And finally, conclusion and an insight. So COVID-19 has taken the world by surprise and has put a tight grip on our lives, our economies, and our well-being. Machine learning and data scientists are racing to help controlling this pandemic by, for example, forecasting the spread, number of confirmed cases every day, every month, and so on, by forecasting the fatalities and cases, death cases, by predicting the impact on economy, for example, the oil prices, the economy at large, and so on diagnosing cases based on the symptoms, diagnosing cases based on X-ray, CT scan, and other modality images, by predicting progress of the disease per patient, and the hospitalization duration needed per patient, and the mortality probability for each patient, and so on, by analyzing vaccine data and vaccine molecular structures, for example, and so on. So these are most of the approaches and the avenues that have been investigated by machine learning and data scientists. And this presentation looks at the COVID-19 challenges that are hosted on Kaggle. And the most prominent and winning machine learning and data science techniques that were used to solve these challenges. Kaggle actually, I chose to work with Kaggle or to present the challenges in Kaggle because it is a well-defined platform and well-structured, and it attracts most of the very talented machine learning and data science researchers because of the challenges, natures, the prizes, and the competition between all of these people and so on. But of course, there are a huge number of researchers and papers and so on that are outside Kaggle. So Kaggle is a subsidiary of Google, is an online community of data scientists and machine learning practitioners, where public data sets are shared and important challenges are introduced. Inside Kaggle, a data scientist can find all the codes and data that are needed to do effective data science work, because people put a lot of data, public data there, data sets, with description and everything, and people put a lot of codes. So on Kaggle, right now, there are over 50,000 public data sets and around 400,000 public notebooks. Notebooks are actually public codes that have description, visualization, and so on. Everything is in Python, of course. So as well, each one of us, you can actually host your own classroom competition, which is called in-class competition on Kaggle. You can put your own data and have a competition which is specific to, you invite only a specific number of people, for example, your students in the class, and the competition can be with prize or without prize. So a notebook, which is also known as the Kaggle kernel, is a Jupyter notebook. It's a Python Jupyter notebook. And the Jupyter notebook, of course, is an open source web application that allows you to create and share documents that contain live codes. You can run them live, and you can put equations, visualizations, graphs, and so on, and text. All important Python libraries are included. So once you want to run your codes on Kaggle, you don't need to install things on your own computer or on the cloud. Everything is already installed, like TensorFlow, Keras, scikit-learn, and so on. Also, which is very important to many of us, especially in places where we don't have much hardware facilities, Kaggle offers free GPU use, which used to be huge. However, from September 2019, Kaggle put a limit on users' GPUs to 30 hours per week, which is still very much sufficient to most of people. About 15% of GPU users go over this limit in a typical week. So how about the COVID-19 on Kaggle? As of October 1st, which is like 3 days ago, 4 days ago, there are more than 40 COVID-19 challenges, which I consider to be a small number. Actually, it's not that much. I expected to see more, but however, there are 40 official competitions that are COVID-19 competitions on Kaggle, and more than 1,900 data sets that are related to COVID on Kaggle, of course. And these data sets come on all types and sizes: images, CT images, X-ray images, some patient information, numbers of confirmed cases and fatalities, and so on. So the main page of one challenge, for example, of each challenge looks very much the same, which is something like this. This is one of the newest ones, which is a vaccine-related challenge. Is a very important one. The prize here, or the total number of amount of prizes, is $25,000. And in each challenges, you find these 6 links: an overview of the challenge, which talks about the challenge in general and the things that need to be done and so on. The data, where you go there and you sign an agreement and then you get the data. Most of the challenges, the data is just free for everybody. And then the notebooks, you are free to start your own notebook on Kaggle, and the notebook related to the challenge, of course. So you can use the data as long as you're doing your notebook on Kaggle, and the data is in Kaggle. You don't need to download anything, and the data will be used directly from Kaggle. So it will be read instantaneously on Kaggle. There is absolutely no communication cost in this case. And then the discussion, which is a very important thing. When you go to the discussion there, you find people starting blogs or discussions on related to the competition. And people are very generous in throwing ideas and suggesting solutions and so on. The leaderboard, of course, each challenge has some public data and then the private data, which will be the final judge. So during the competition, the leaderboard will measure the success of each team submission based on the public data. And then after the private data is published or given, then everybody applies their technique on the private data, and they get the scores, the final scores, which actually shows the winner, the first winner, second winner, and so on. So they put everybody with their scores and their rank and so on. And the rules, of course, are the very general rules of no plagiarism, no cheating, and stuff like that. So how about the classification of the COVID-19 Kaggle challenges? When I went through all the Kaggle challenges, we can actually divide them into 4 categories. First one, forecasting challenges, which basically try to predict number of new cases of COVID-19 new cases per day or per week or per month with a different horizon. So for example, a week from now or a month from now or 2 weeks from now and so on. Number of confirmed cases and number of fatalities. And then the second class of challenges, data analytic challenges, which does not specifically look at predicting new cases. These are more classification and regression problems, which I will talk about some of them. For example, it would try to predict the oil prices, for example, during the COVID-19, or try to predict if a specific patient, how many days that patient will spend in the hospital, or what is the probability of mortality for that patient, and so on, based on some symptoms, which some of them may be numeric and some not. Third category, image classification challenges. And these are where probably 75% of everybody working in machine learning and data science go to this thing, X-ray images, CT images, and they try to classify if this patient is, for example, has viral pneumonia or bacterial pneumonia or a COVID-related pneumonia or nothing at all, and so on. And then image segmentation challenges, which try to find and localize affected areas in the lung that are COVID-related. So this is more like semantic segmentation or pixel-wise segmentation. So if we start with the first category, which are the Kaggle forecasting challenges, we're trying to forecast things like that. So these are actual data for different places, Canada, United States, Italy, Japan, Spain, and so on. Starting from the beginning of counting the cases. I'm sorry. So what is required is that you are given this amount of data, for example, which is 2-week data, 3-week data, 1-month data, and then you are required to predict what will happen tomorrow, what will happen next week, what will happen 2 weeks from now, and so on. So these are basically time series prediction, forecasting challenges, okay? And the horizon may differ from one challenge to another. There are 9 challenges, and there were couple more challenges, but were private. So they were what we called in-class challenges. So I couldn't see the data, but 9 of them are, these are public challenges, which are 5 of them are very related to each other, which are called the 1-week challenges. And these 1-week challenges, you are given only 1 week to develop your models. So you're given some data, you have 1 week to develop your model, and then the test is just on the 8th day. So they did 5 of them. Okay. So what is the challenge problem in this case? These are multi-dimensional, multivariate regression problems or time series prediction, where you have m-dimensional inputs and they are mapped to n-dimensional predictions. The m, which are the inputs, depend on the number of variables used. So for example, you can use the number of confirmed cases today, yesterday, and so on. So you have your window, your prediction window for the number of confirmed cases, the number of death cases. You can introduce, so they allow the competitors here to get or to outsource other sources of information. So for example, the region information, which is given in the data, most of the data, the region information, which is the location of the city, for example, or the country, the awareness level. So is this country, for example, or this state COVID aware, and what is the awareness level? The shutdown level, have they shut down everything or partially, or they didn't do any shutdown? The percentage smoking, the number of doctors, the number of hospitals, and so on. You can introduce whatever information you like if you feel that they will help you in the prediction. So some teams did, some teams didn't, and so on. While at the end, what you're required to predict is the number of confirmed cases and the number of fatalities for a given horizon. So usually you're required to predict, for example, for 1 month ahead, every day in that 1 month ahead. And these are the inputs, which are the number of confirmed cases, number of fatalities with a specific prediction window, and any external input variables that you like to have. And then you have to develop your multivariate regression model. So for example, the 1 week challenges, which were 5 of them, these are the number of teams that contributed in each of these challenges. And it was required to forecast daily confirmed cases and fatalities, as I said. These are the data durations that were used in the 5 challenges. So in the first one, for example, it was between the 22nd of January when they started counting cases, and the training data is given up to the 24th of March, and the testing is between 25th of March and 22nd of April. And this data, the training data, you are given only 1 week with this training data to predict models. And the models, you're supposed to predict models for many different regions and many different countries. So many different countries and many different states in the United States. So the issues of concern in these challenges, first of all, small amount of data, specifically or especially in the early stages, in the week 1 and week 2 and week 3, when we didn't have a lot of data at that time, and specifically for certain places, maybe China and other places, they had numbers, but other countries, they were still having, for example, 1, and then a couple of days 0, and then 1, and so on. So it was very difficult to create models for such countries, but it was required in the challenge. So when you have very little amount of data and a lot of zeros, you get overfitting, you get unstable models, and so on. Also, the feature importance and ranking was a very important thing here. A lot of people discussed about it, which is if you are going to use external sources, which external sources, which is the percentage of smoking, number of doctors, the actual region, location, and so on, which of them are important, which are not important. If you use a lot of unimportant features, you're gonna get bad models and you're gonna get overfitting and so on. And then your multi-step ahead strategy, because you are supposed to predict in the challenge 1 month in the future or more than that, every day in that month. So this is what we call the multi-step ahead time series prediction. So people use different things. They used MIMO, which is multiple input, multiple output, like a one big model with the multiple inputs, and you have the multiple output for each horizon. Some people used a separate model for each horizon, and so on. Some people use the recursive model, so they take the prediction of tomorrow, they use it as an input for the prediction of the day after, and so on. So you have a lot of different strategies that have actually been used by different people. You also have the many region issue. So definitely there is a correlation between the number of confirmed cases, for example, in China and Vietnam, between the number of confirmed cases in the Italy and Spain, probably. So should you use one model for everybody and have a different output for each region or each country, or you should have a separate model for each region? That was also a challenge by many people. This is an example of the data. So for example, this is a snapshot of some of the data for Afghanistan. Here you have the locations, here you have the dates, and here you have for each date, you have the confirmed cases and the fatalities. This is data, for example, for state of Maryland in the United States. For example, that's what I meant by having a lot of zeros. So in the beginning of your data, of your training data, you may have a lot of zeros. This is very nasty data to use in modeling. This is even worse in this case in Zimbabwe. Even in 20th of March, they still had a lot of zeros and confirmed cases and fatalities, and then just you get 1 and then zeros and then 2 and then zeros and so on. So these are all very practical problems that appear in practical data sets. So looking at all the leaderboard and the discussions, and fortunately in Kaggle, they give you the rank of each team. So these are the best techniques or the most prominent techniques that have been used or have proven to be very effective in the forecasting challenges. I put them there, not actually in, probably in the reverse order. Statistical methods, people used sigmoid fitting, and sigmoid fitting techniques were ranked, they reached rank 15 and 39. Linear regression, they got 6 and 10, so they were from the top 10. Random forest, 7 and 8. Deep neural networks, ranked 4. Gradient boosting machine, where most people use the light GBM, the light gradient boosting machine implementation. Actually, this is a very much a data science. Data scientists like and love gradient boosting techniques, and they still are doing extremely well in practical challenges, forecasting and classification. So they beat deep neural networks in this challenge, in this forecasting challenge. So I'm going to talk about each one of them briefly. Sigmoid fitting or logistic growth fitting, which is a very old technique, and people like to use it in modeling natural growing phenomena like disease, for example, and pandemics, where you actually have a very fast growing in the beginning, and then it starts to saturate with time. But however, of course, as we can all see now in the United States and Europe and so on, there is a second wave. So now we have another jump. However, this is the equation for the sigmoid, which has very small number of parameters, which are the K and R. People usually use least squares optimization or least squares fitting to estimate the parameters of the distribution, which is the sigmoid distribution or sigmoid curve. And most people use the Levenberg-Marquardt algorithm, which is the most efficient one to solve this problem. These are actually the results from the competition. So here is the actual data, and here is the estimated curve. Okay. So it looks very much like a sigmoid function in that particular time of the competition of the data set. So as I said, this one is very simple, very quick. However, it didn't really reach the top 10 in the competition. So it's so simple, small number of parameters, very efficient algorithm. The data supports the sigmoid shape. However, you cannot really include external sources of information doing this very simple sigmoid modeling regression. So other sophisticated techniques actually did well. Linear regression, it obtained rank 6 and 10, which is very good, and very high rank. In linear regression, actually, they use multivariate regularized linear regression model, where you actually have M, in your input, you have M variables or M features. These M features, they could be the prediction window, where you have the number of confirmed cases for M days, or you can have number of confirmed cases plus other external sources. So in this model, you can include your X here doesn't have to be from the same nature of what you're trying to predict. It could be other features as well. We use regularized least squares modeling to avoid overfitting, and most people use the L2 regularization. Some people use the L1 as well. However, the people in rank 6 and 10, they use the L2 regularization. However, as we can see, the number of cases, if you look at the number of cases per day, it looks more like a Gaussian distribution. The number of cumulative cases or accumulated cases, they look like a sigmoid or like a raised, like a capacitor charge function. So how come they use a linear regression? Actually, they model the daily cases as this capacitor charge equation and the fatalities as well with different parameters. And then actually they subtract the starting value. So here we have the starting value, you can subtract the starting value, and then you can take the log. So once you take the log of these equations, of these values, it becomes linear. So when they subtract the starting values and take the log, both the daily cases and fatalities become linear in the time variable. Thus, they use linear regression. So that was the trick they did. They subtracted the initial values, and then they took the log, and then they used linear regression models where the input were the log of the daily cases with a certain prediction window, and the log of fatalities with prediction window. And what they try to predict are the log fatalities of the horizons required and the log daily cases. And this, as I said, worked very well. We got very good ranks. And the linear regression, of course, is also very nice because you have huge number of very well-established libraries that you can use. And this is one example of the rank 6 team, where you have this, the green curve is the difference between the confirmed cases, which is the blue, and the fatalities 8 days later, which is the orange. So they found that the fatalities are highly correlated to the confirmed cases with a lag of 8 days. Another approach, which is the random forest regression models, these obtain the 7th and 8th places. This is also a very well-known data science technique that people of data science and machine learning love it very much, like it very much. Of course, a decision tree has a huge advantage, which is it can deal with numeric features and non-numeric features, which are called the categorical features, seamlessly. So, for example, in this case, when you're growing a tree, here, for example, it's asking a question about a categorical feature, if the person is married versus single or divorced. This one, for example, is a binary feature, yes or no. This one is a numeric feature. And then you reach your prediction, whether it's a 5.5 or 2.3, if you reach this leaf. So a random forest is a collection, 50, 100, 150, for example, different trees that are working in parallel. So you train or you grow each one of these trees. However, to avoid having a copy of each other, each tree is trained on a random 63% from the data, from the training data, around 63%. Or around that value, you can actually choose this value, and it is actually tested or validated on the remaining part of the training data that it was not used to be trained with. And then finally, when you have all these trees, each tree has a weight which depends on its performance on its out of bag data, which is its validation data. And then you can actually combine their value or their predicted value using a weighted average to get the final outcome. So this random forest model is very efficient in classification and regression. It's very smooth, and it deals seamlessly with categorical variables, and it behaves gracefully with small amount of data because of the aggregation thing. So it actually averages out all the noise. However, it reached only 7th and 8th places. The 4th place was by a deep neural network. So that was the only deep neural network which got a top 10 place. The people here used one-dimensional CNN. CNN is an abbreviation for convolutional neural networks, which I will talk about later in the image processing part. In this case, for example, they have a 14, the input vector has a 14 values, fatalities, and 14 values confirmed cases. So if you focus on the confirmed cases, they decided to have 8 filters or 8 neurons with a stride of 1. And in these cases, these 14 days, when they did these filters with a stride of 1, they obtained a vector of 12. So here we have 8 vectors, each one of length 12. And each one of the 8 vectors is produced by a different filter or a different neuron. And each neuron here has 3 values. As you can see, each neuron has 3 weights. So that was the first level. So all these weights, of course, are trained using the stochastic gradient descent training or the backpropagation training of the network. And then the second level, they decided to have 4 extra neurons for each of the 8. So now we have 32. So it's like we have 32 different feature maps. Okay, and each one of them now has a length of 4. Okay, because now they used a stride of 3. So now we have 32 vectors, each of length 4. And then they have another 4 neurons. So each of the 32 feature maps is applied on 4 neurons. So now we have 128 vectors, each of length 2. So now we have a vector of length 2, but 128 of them. Now they concatenate all these guys to have a total vector of length 256, which from this point up to the end behaves like a multi-layer perceptron old-fashioned neural network, where you have this is your feature vector, and you're trying to predict the fatalities and the confirmed cases. Actually, they use what is called the pinball loss, which is a quantile regression. The quantile regression, they use 3 quantiles, 5%, 50%, and 95%. A lot of people now move into the quantile regression because, and they actually at the end, they use the 50% quantile because it tries to estimate the median of the data, not the mean of the data. So it is much more robust against outliers. So this is what they did actually. And they used the 50% quantile. Now to the winner. The winner of this challenge actually was the light gradient boosting method. And the LGBM, or the light gradient method, is just a gradient boosting or a tree gradient boosting technique or framework that uses boosted trees based learning algorithm. The LGBM is an efficient implementation of the gradient boosting. So we are going to talk about the gradient boosting, and the light GBM is only just a quick and fast and parallel implementation that runs much faster. Surprisingly, this technique obtained the 1st, 2nd, and 3rd places, and other places in the top 10 as well, which says a lot about the reliability and robustness of this technique, especially for this type of actual data where you have a lot of missing values, a lot of zeros, and so on. So the gradient boosting regression, in the training, they start by getting the average value of the target, and then the first tree is trained on the residual between the average target, which for example is 71.2, and the target of each example. So for each example, you get the residual between the actual target of that example minus the average target of everybody. So this is like the residual, and this is the first tree. This is equivalent to a gradient. That's why it's called gradient boosting. And then the second tree is trained on the residual between the actual target of each example and the predicted target for each example using the first tree. So now you have the average value plus the first tree. You combine this value with the predicted value from the first tree, and then you subtract that combined value with the target, and then you get the residual that you're going to train the second tree, and so on and so forth. So for the third tree, you combine the average value plus the predicted value from the first tree, predicted residual from the first tree, plus the predicted residual from the second tree. You combine all this to get a predicted value. You subtract that from the actual value, you get new residuals, you train the third tree, and so on. And this 0.1 value is the learning rate. So the learning rate, you can keep it a constant, or it actually can be data determined by cross-validation or whatever. And the number of trees, so how many times you're going to do this, this is also determined by cross-validation. So you keep doing that, and every time you test on your validation set, which is a separate part from the training set, and then you stop when you start to overfit. In the testing time, when you have a new pattern like this one, for example, and you want to get the prediction, so the prediction will be the average value of the targets where you got from the training data, plus the residual prediction from the first tree multiplied by the learning rate, plus the residual from the second tree and the third tree, and so on. So just the same way as you did in the training data, and then you get the final result based on how many trees you have. So this gradient boosting regression is also an ensemble technique like the random forest. So it has this very strong smoothing, robustness against noise, robustness against the small amount of data, and so on, and it produces extremely strong results. Also, these guys, the first place guys, they used quantile regression, and as we can see, this is the actual data, the blue, the training data, and the green one is the 50% quantile. The purple is the 95% quantile. The red is the 5% quantile. So basically, they use the 50% quantile, or they take an average of the three. Some people do that, some people don't, and so on. So as we can see, the 50% quantile is a very smooth continuation to the actual data. Now we finished the first category of challenges, which were the forecasting challenges. Now we talk about the second category, which is the data analytic challenges. Here we had something like 6 challenges or a little bit more, which were private. The first one, you're required to classify if the person is COVID-19 positive or not from a list of symptoms and test results, for example, blood test results, and so on. The second one, mortality probability of an incoming patient based on the symptoms and other patient-related, like travel history, and so on. So here we start to see some features which are completely non-numeric, and some features could be missing. Here you have to estimate that the changes in the COVID-19 hospitalization, for example, the general number of beds, the ICU beds, and so on. In this one, evaluate which factors affect the spread of COVID-19. Here you have a prediction of oil prices in COVID-19. This one is the most recent competition, which actually to try to predict the likely degradation rates at each base of the mRNA molecule of certain vaccines. The problem here is that the new trend in COVID-19 vaccines is to try to insert the RNA, the useful RNA part of the virus, so that the body will start to generate antibodies for the virus based on that part. The problem is this RNA part is very volatile. It degrades very quickly in room temperature and so on. So here in this challenge, they try to know which parts of the molecular RNA stream, which parts actually are the most degradable, which parts cause the degradation, so that they can use this to try to choose a more stable part of the RNA. So these data challenge problems, the data analytic, these are mainly classification and regression challenges, and they are characterized by having mixed variables, categorical and numeric. Potentially, there may be a huge number of missing values for each record. For example, you can see this is one of the challenges. As you can see here, this feature here, for example, has a lot of zeros, and then you have a 1 here, and so on. A lot of features are not existent for many records. However, they exist for some records, and so on. This one, for example, is for the mRNA prediction problem, where you have the first feature is the ID, second feature is the sequence. So here you have the sequence of the A, G, C and U symbols. And here you have the structure, which is a stable or non-stable structure, and so on. So here we have some features are basically sequences, like these two. Some features are numbers, and some features are integers, and so on. So you need to have your model, which should be able to handle all these types of features. So again, the boosting trees performed very well in patient diagnosis challenges. So all these challenges that were here, from 1 to 5, the XG boost, which is the extreme boosting classification and regression techniques, were number 1. They performed the best. However, deep neural networks also performed very well in some of the challenges, and particularly in the last challenge, which is the vaccine challenge. Everybody is working with a deep neural network because it is very able to work with the sequences, as we can see now. So the XG boost for classification, which is called the extreme gradient boosting, it works very well. It is very much similar to what I described before about the gradient boosting technique. However, this one is for classification. And the extreme gradient boosting is another very efficient implementation where they have cross-validation, weighted quantile, sparsity, and so on, regularization, and so on to get the best performance. So the XG boost actually takes a very small training time compared to the gradient, the normal gradient boosting, and it performs a little bit better or very similar to the original gradient boosting, much better than random forest and logistic regression and other techniques. Now let's talk about the neural network approach. So the neural network approach actually, the deep learning approach and the new techniques in neural network are very interesting because they are able to handle categorical variables. So symbols and sequence of symbols and so on. How? By using what is called the one-hot encoding implementation or one-hot encoding technique. For example, if you have a symbol that can take 4 different values, A, C, G, and U, for example, then you can have a vector of 4 dimensions. And if it's an A, then the first one will be 1 and the other 3 will be 0 and so on. And then this vector here, for example, suppose now you're taking a window of 3 symbols. So this is the first symbol. So you introduce it with the one-hot representation, and then the second symbol, and then the third symbol. And then here you try to predict something. So for example, you have this window, and you know that this part, for example, is a sick person or a normal person and so on, or this is a good part of the RNA or a bad part of the RNA based on the true ground truth you're given. So this is your input, and here you have hidden layers, one hidden layer, and then dense layers, and then your output layer. You can do classification or regression and so on. So this is a very seamless and very nice way and very efficient way to introduce categorical and symbolic variables in the neural network domain. And what is very nice also is that you can have here, for example, you have 3 symbolic or 3 symbols, and then you can have other inputs. You can have numeric inputs or whatever type of inputs to the same neural network. So your neural network now has the symbols, numbers to the left, numbers to the right. So the context as a whole is being modeled by the neural network. So that's why this embedding neural network techniques are now working extremely well in this competition with the RNA, because they have the symbolic strings, and also in many time series forecasting competitions where you have some of the features are numeric and some of the features are symbolic or categorical. And now if you're actually trying to predict a sequence, so your decision actually is not a snapshot. You have to wait until you finish the whole sequence. So for example, your sequence has 20 different symbols. Now you have your window moving around the sequence, and then you have to finish until you finish the 20 sequence to get the classification. Then you need an RNN, recurrent neural network. So your embedding layers will feed a vector here. You have this output vector coming from this dense layer, or you have the output feature vector. And then every time you move your window, your feature vector will have a new feature vector. So this goes into an RNN, recurrent neural network, which could be a traditional RNN, or could be an LSTM, long short-term memory neural network, or or gated recurrent neural network, and so on, or a transformer neural network, so that you're actually modeling the sequence. So this is a typical structure that is being used actually in this competition. Now, let's move to the third category of competitions, which is the image classification challenges. And a lot of people like and love to go to these challenges because computer vision image processing is very popular. And you have a huge number of pre-trained models. So you have these 4 competitions so far: chest X-ray, and this X-ray, X-ray, and X-ray. So these 4 are X-ray data, and it's required to basically know if the patient is sick or not, has COVID or not, or what kind of pneumonia does the patient have, and so on. So these are examples of the X-ray images used in that particular challenge. This is one challenge, this is the other. So here, for example, you have this normal person, you have the COVID-19 and SARS. Here you have also COVID-19, pneumonia, TB, and healthy persons. So that's what you're required to feed your machine learning technique an image, and the machine learning should classify the image to be one of these 4 categories or one of these 3 categories, and so on. So the best models that people have used in the competition are basically pre-trained convolutional neural networks. People have trained deep CNN models for the last maybe 10 years. So you have pre-trained models, and the objects of these pre-trained models, you can find them in Python, in C++, in MATLAB even, and so on, like AlexNet, VGG with different versions, ResNet, DenseNet, InceptionNet, SqueezeNet, and so on. Each one of them has many different versions. So the people in the competition use these in 2 different approaches, either as a feature extraction. So they use the pre-trained part, and then they take the output from certain layer as features, and then they introduce the features to some other machine learning technique like XGBoost or random forest, or they actually take the whole deep neural network and then they insert their own head, and then they fine-tune the head of the neural network, and then they probably can fine-tune the whole neural network. So this is the basic CNN model. You have the input image, you have the first layer, convolution layer, convolution with ReLU, and then you have pooling layer, which usually people use 2x2 with the stride 2, which reduces the image to half the number of rows and half the number of columns. And then you have another convolution layer with ReLU and then pooling. And finally, you have the output layer, which usually 1 or 2 fully connected layers with the outputs as a softmax if you're doing classification, or just usual output, linear output if you're using regression. So these are actually what have people used in the competition. Some people use the ResNet, and this is the first technique, which is as a feature extraction. So they used ResNet, and people used other pre-trained neural networks. So this one is already pre-trained. They take it as it is, and they take the features for all the training data, and they train a machine learning classifier, random forest or XGBoost, and so on, and they do the classification. The other technique, which is a fine-tuning of the whole architecture. So they take a pre-trained model, and then they insert a head output layer, 1 or 2 fully connected layers, and then they do fine-tuning. And actually, this was a paper in August, just a couple of months ago, which is a comparative study of this second technique, which is actually they took the pre-trained model, and then they inserted a head, which is a fully connected layer, and then they fine-tuned the whole architecture. And as you can see, they used AlexNet, DenseNet with different versions, Inception, ResNet, and so on. And these are the classification performance for the different classes: COVID, no pneumonia, non-COVID pneumonia, and so on. And these are the final results. So as we can see, most of them obtained very good results. Probably the DenseNet has the best results over all the techniques, but not very significant changes, which means that the idea of using pre-trained models worked very well in the X-ray competitions. Now, the final class of competitions is the image segmentation challenges, which is actually only one of them. And this is using CT images, computer tomography images, or CAT scan images. And the guys who did the competition, they classified the different cases into 6 cases where you have, first of all, you have no COVID at all until you have very advanced COVID situation, okay? And the challenge, based on the CT findings, the level of suspicion COVID-19 infection is graded from very low to very high. The objective is to segment 2 findings in the lung, in the CT of the lung. One of them is called the ground glass, or GG, and the other one is called consolidation, which are 2 types of lesions that are found in the CT of lungs. So for example, these are almost clean images. Here you have no ground glass and no consolidation lesions. Here, for example, you have very bad cases where you have a lot of consolidation and a lot of ground glass. This is multifocal GG and multifocal consolidation, and this one is PCR positive. So what is required in the challenge is that the image is the input to the machine learning system or the deep neural network, and the deep neural network is supposed to segment per pixel. So you need to know which pixels are GG and which pixels are consolidation. And finally, we want to calculate the volume of the GG and the volume of consolidation, and to rank if this person is, what kind of infection or what level of infection does the person has. So this competition actually is not done yet, so we don't really know who is the winner. However, everybody's using the UNet. Almost everybody is using the UNet, which is an advanced version of the FCN. UNet is based on the fully convolutional neural network, which is the FCN. So this is the FCN. In the FCN has 2 parts. The first one is the convolution part. The second one is like the deconvolution part. So the trick or the idea is that in the training, during training, here you have your input, which is an image, and at the output you have the mask of the image, which specify exactly which pixels lie in which category. So for example, you have, if you're trying to segment the GG and the consolidation, GG, for example, you would give the pixel category 1, consolidation category 2, the background, for example, category 3. If it's in the lung, category 3. If it's outside the lung, category 4. So maybe you have 4 categories in this case, which 2 of them are very important for you. You need to obtain them. So what people use, the UNet architecture, which is like an FCN. Okay, here is the convolution part, and here is the deconvolution part. However, in order to maintain the very important information, because during the convolution, a lot of information is lost, which is the position of the pooling. When you're doing the pooling, the position of which part you actually took and survived. So in order to maintain this information, you do lateral copies from the convolution path to the deconvolution path. And this lateral versions of the feature maps can actually be weighted by certain weights, and they are used during the deconvolution to produce the best results. So this UNet actually produced the most efficient results, or the most optimum results in the image segmentation, which is the semantic segmentation during the last couple of years. So everybody's using this one. Now we finished talking about the 4 main categories. So if we look at the COVID-19 data sets on Kaggle, as we can see here, a lot of data sets are basically patient information. So these data sets actually are not necessarily in the challenges. These are just data sets that people put, okay? So they put for public use or for people to use together, collaborate in these data sets and so on. So you have all these data sets are just numbers, usually number of confirmed cases and fatalities from different parts of the world. And then you have a couple of data sets, not a couple, I mean a couple of hundred data sets, which are images, PNG and JPG. So also these are mostly X-ray and CT data sets. So Kaggle, as I said, is just one platform, one instance, but however, it is the most structured and most important platform for machine learning and data science researchers. However, if we start to look at Google Scholar paper search and do a search on COVID-19, we got more than 1,300,000 total COVID-19 papers. However, a huge number of these papers are from the medical, completely pure medical domain. So when we start to look at COVID-19 with computer science, you get around 279,000 papers. So these are 279,000 papers in the last, we have only 8 months, less than 8 months since the pandemic started and people started to get actual data to do papers. Of these papers, you have around 12,000 on deep learning, 3,600 image classification, image recognition, image segmentation, prediction of confirmed cases and fatality, generative adversarial network, which is the GAN, which I'm going to talk about in 2 minutes. So these are most of the papers that have been produced on COVID-19, which means that people have been extremely active in this area. However, not very coordinated. So if we talk about GAN, why I talk about GAN? Because it is probably one of the most interesting and important deep neural network techniques that can be used in the COVID-19. The GAN, or conditional GAN, conditional generative adversarial network, which looks like this, has a generator and a discriminator. The generator in this case, suppose that you want to use this for COVID-19. The COVID-19 problem is that you don't have sufficient amount of data, images, for example, and even forecasting data and so on, to predict and to classify and to train machine learning models. So most of the people who used GAN, or GAN, they used it to synthesize or to augment their training data. So this one here, for example, we want to generate images. We want to generate a lot of X-ray images or images that look like X-ray images with people with COVID-19 pneumonia. So you train this network such that if you want to produce a COVID-19 image, you put a condition of 1. If you want to produce bacterial pneumonia, you put it 2. If you want to produce viral pneumonia, non-related to COVID, you put it 3. If you want to produce normal X-ray, you put it 4. So this is like a condition. And then you feed it with random noise, and this is like a CNN network or an FCN network that we talked about, which has the input like a random noise, and it produces an image. So the discriminator starts to feed back the generator and tell, okay, now the image looks very similar to the actual image or not. And once this network learns, now you can take the generator and use it to synthesize and generate new data. So a lot of papers have used this technique in the last couple of months to generate synthetic and augment their training data by doing images or audio, for example, like the sound of the chest in COVID-19 and so on. So for example, these are examples of generated images from the GAN in a paper that was just released in October this month. So to conclude, in almost 8 months, data scientists and machine learning scientists have produced around 279,000 COVID-19 related papers. Kaggle is taken in this presentation as a platform for a more structured and organized efforts. we have around 40 challenges and 1,900 data sets that are COVID related on Kaggle. Most research on Kaggle and otherwise focused on forecasting confirmed and death cases and on image classification. So what is the insight? What is missing? Definitely we need more effort. More effort should be put on health records and vaccine and medications. Health records, for example, patient health records, the symptoms, the background, the history of the patient, and so on. And what does this specific patient need? Does this patient need to be hospitalized or not? What are the optimum medications for that patient, and so on? And also more effort need to be put on vaccines. So far, I have seen only one challenge that is related to the vaccines. So the people from the medical domain and the people from the AI domain, they should get together more in order to make the vaccines more efficient and faster. And there should be more organized efforts. For example, more challenges on Kaggle and other platforms. For example, the Grand Challenges platform, which is a known biomedical platform. Right now, it only has 3 related COVID data sets only. The research should be more proactive and long-term. So for example, we are starting the second wave in Europe and the United States and so on. So how about the prediction of the second wave and what will happen after? How about the prediction of the effect of the vaccination on people and societies? The effect of different shutdown scenarios. Should we shut down completely or partially and so on? And what will be the effect on the health of the people? What will be the effect on economy and so on? The effect of opening schools and so on. There is more collaboration that is definitely needed between medical research centers and AI society, and more effort should be done to use the AI for quick and fast COVID-19 diagnosis and to determine the hospitalization need and medications needed for each patient to avoid complications. So these are some of the references I used. Thank you very, very much, and hope to see you all in good health. Thank you.